Good day, we are the Group 7 here to talk about the Hartley oscillators. First, we need to know what are oscillators. Oscillators generate a continuous periodic waveform at a precise frequency by converting a DC input into an AC output. This waveform varies in wave shapes and frequencies. Basic LC oscillator circuit is a type of oscillator where a inductor-capacitor tank circuit is used for giving the required positive feedback for sustaining the oscillations. But these circuits have no means of controlling the amplitude of the oscillations and also have a difficult time in tuning the oscillator to the required frequency. Therefore, we turn to the Hartley oscillator. The Hartley oscillator is a type of harmonic oscillator invented by Ralph Hartley back in 1915. These oscillators are tuned circuit oscillators which are used to produce good quality sine wave signals in the range of frequency. Its frequency of oscillation is determined by the tank circuit, which has a capacitor connected in parallel with two inductors connected in a series, commonly called a single-tapped inductor. These oscillators are available in many different configurations like common emitter or common base configured and BJT or FET amplifier based. The frequency of oscillations can be calculated in the same way as any parallel resonant circuit using the formula of the parallel resonant frequency presented in the PowerPoint. We then turn to the advantages and disadvantages of using a Hartley oscillator. The advantages are as follows. The need for components is very less even after including the top coil or fixed inductors. Frequency of oscillation can be varied by varying the inductance or by using a variable capacitor. A single coil of bare wire can be used instead of using two separate inductive coils. The amplitude of the output remains constant over the working frequency range, and the sinusoidal oscillations with constant amplitude can be generated in the Hartley oscillator. Following that is the disadvantages of using Hartley oscillator, which are sometimes distorted sinusoidal signals will get generated due to the presence of harmonics. The harmonic content in the output of this oscillator is very high, hence it is not suitable for applications which require a pure sine wave. The Hartley oscillator can't be used as a low-frequency oscillator since the value and the size of inductor becomes larger. Next up is explaining the Hartley tank circuit.
So we will now present to you a Hartley oscillator simulated in LT-Spice. For our Hartley oscillator, we have a Hartley tank circuit connected to the main oscillator circuit, which is located at the bottom. This consists of a capacitor connected in parallel to the series connected 0.23 microhenry and 2.3 microhenry inductors. The tuned LC circuit is connected between the collector and the base of a transistor amplifier. As far as the oscillatory voltage is concerned, the emitter is connected to a tapping point on the tuned circuit coil, therefore producing sinusoidal waveforms when simulated.
Okay, so after discussing the circuit diagram, it is now time to simulate our Hartley oscillator. Now, before we do the simulation, we must first configure the simulation configurations. So we will press this one, and okay, so we have here the edit simulation command box. So we will do a transient analysis with a 30 millisecond stop time. So let us go. Okay, now when we simulate, we will measure the output voltage here. And as you see, we see a sine wave, a series of sine waves, a thick series of sine waves in the simulation. Now, so as we wait for the simulation to finish, as we observed, our oscillator is composed of components that are typical components of an oscillator. We have here capacitors, we have here resistors, and the most important component is the transistor. Okay, so what we are using is an NPN transistor, a N222 transistor. And we have here a tank circuit here in the bottom. Now, as we wait the simulation to finish. Okay, so we have here the resistors and here's inductors. Okay. It's quite taking some time. And okay, we're done. Okay, it's a final sweep for the simulation. So this is, as we can see, as we observe, this is a sine wave, and this solid green is a solid frequency wave of wavelengths output by voltage in the Hartley oscillator. Now, as you can see, we have here the RMS. We have a 24.15 volts of RMS, and as we zoom in, we will see the waveforms here. So as we can see, we can now see the high frequency of the waveforms, and see these are the peak values. So you see more. Okay, so that concludes our report, and thank you for that would be all.